In our previous sessions, we were primarily looking at in a data, how do I make the mean, median, the central tendency, the deviation measures, the skewness and the kurtosis, the calculations of these elements. And we also looked at how do I use this statistics into the probability world, the relative frequency getting translated into probability, and then observing some of the most common probability distributions. Now, the next world goes into how do I make some kind of inferences from the data. See, the most important part of statistics is with the data, which is typically we call as a sample of data. With that sample of data, how do I make some kind of conclusions or interpretations about the complete population? That's the major intention of using statistics. So calculations is one part, but based on the calculations, how do I make conclusions is the most important part, right? And that is what we are going to deal with in this session, in this chapter, as well as the next chapter, which is hypothesis testing. These two are more targeted towards you making some kind of calculations on the sample, and using that calculations make some kind of interpretation or inference about the population of the data, right? And what statistics simply says is, in order to get the best inference about the whole population, choose your sample as much random as possible. Let's say I'm talking about finding out the average height of an Indian male, right? Or the average return which a particular stock can give on a single day, right? Now, if I choose all the days where the returns were very high and take the average of them, probably my average would be a very high number itself, and my interpretation will come out like the average return which Infosys gives per day is going to be something very high. Or if I take very low values only, then it gives me that the average is very, very low. But if I take some 50 days at random, completely use whatever logic you want, right? There are something called random numbers generators also available. In a random way, pick out some 50 days and find out their average, right? That is what is the true reflection, or it takes you closer and closer to the population's actual average, right? That is the intention behind doing an estimation, right? Sample and then making an inference about a population, because at the end I cannot collect the data of the entire population. If I have to measure the average height of an Indian male, I cannot go to each and every male and measure his height. It's literally difficult. By that time, someone else's height would have gone up. So, literally, this is not possible, right? So, I have to work with a sample of data itself, or even a stock's daily return. What is my definition of a day? 12 o'clock today to 12 o'clock tomorrow also is called as a day only. Morning to evening is also called as a day. So, again, the definition of the day, so I can have so many possibilities. So, literally, I cannot go and collect each and every possibility. In that case, it's better for me to work out on the samples. If the sample is as much random as possible, it will reflect the population in a very effective manner. So, from that standpoint, again, we have 2 or 3 different kinds of samples which we discuss in this chapter here. We talk about simple random sampling as well as stratified random sampling. Simple is more blind. Out of the whole set that is available, whole data that is available, I'll pick up some 1,000 people and measure their heights. I don't bother who are those 1,000. That is simple random sample. But if I'm talking about a stratified random sampling, I will divide the whole data into groups, probably state wise, or North India, South India, North, East, South, West. So probably let me pull out some 200 people from West, 300 from North, 400 from South, 100 from East. So what I'm doing, random only, but I'm making a randomness within a subgroup. So probably again, if I want the people, old people versus young people, the heights. Again, it's better, instead of randomly picking some 1,000 people, it's better that I pick up intentionally some 800 young people and 200 old people. If that if that proportion is more or less in the same proportion of the entire population. If I say youngsters are 80% in the overall population and oldies are 20%, so even your sample also let it be picked in that same manner. Out of the 1,000 you would like to pick, divide them into older generation and younger generation, pick 800 here, 200 here, right? So in that way, whenever you are trying to pull out your data, we are calling it as a stratified random sampling. So these are two different methods. In some cases, a simple random sampling is very much required for me, and in some cases, a stratified, let's say male versus female, I have to do some comparison. It's better that I have sufficient amount of male data as well as female data. If I randomly pull out, I don't know, I may get all male data or may get all female data. All these are different possibilities, right? So from that standpoint, we look at the stratified random sampling itself, right? Okay. So wherever we are taking a sample of data, we know that there will be a difference definitely between whatever the sample calculates. Say I have taken a sample of 1,000 people and measured their heights, and I will find out their average height. Obviously, there could be some difference between the average height which my sample is telling versus the overall population's height, average, right? That difference which is existing in my sample when I compare it with the population is what I call as a sampling error. That is what I am calling as a sampling error. The difference between the population value and the sample value. Any calculation I am doing on a sample, let's say average. Any 1,000 people I am taking, right? I take these 1,000 people on a random basis itself. I may get some average height. Probably that 1,000 I take, I may get slightly different average height. So what is happening is the sample average is itself is a different values. If I take the average of this 1,000 people, I get one value for the average. If I take the average of the another 1,000 people, I get another average, right? So that average itself keeps changing, which means it itself is a random variable. It's a random value, average, with for this set of 5 people, if I take the average, probably the height is 160 centimeters. For this set of 5 people on a random basis, I take the average, it may be 165 centimeters. For another set, it may be 200 centimeters. So because the value of the average itself keeps changing with the different samples which you are picking up of the same size, what we say is the sample value itself, sample mean or sample standard deviation or sample, any calculation you do on the sample is itself a random variable. Random variable means it also has a distribution. It could be a normal distribution, it could be a binomial distribution, it could be something. Any random variable, in our last class we have looked at, any random variable we can associate it to a distribution, right? So depending on whether it is discrete or continuous, We will associate it to a binomial distribution or a normal distribution or any of those things. Correct? So that whatever the sample value is calculated, sample mean minus the population mean, whatever I am talking of, we call it as a sampling error. And the sampling distribution tells me how my mean is going to change. 165, 160, 170, 180. There are some chances that the mean can be below 160, mean height can be below 160. There is a little chance that the mean height can be above 190. So it talks about not one single value, it talks about the parameter or the calculation of the sample or the statistic that is being calculated on the sample. Right? So when we get into this process, any data which we start looking at, we classify it either as a time series data or a cross sectional. Very simple. Whenever we observe a data which has a time angle in it, what is the time angle? Monthly data or yearly data or daily stock prices. Such kind of data where there is some element of time, time wise, equal intervals of time, the data is captured. We call them as time series data. And for a particular point in time, I gather the data of various entities. For example, today's stock prices of 50 companies. So it's not the stock price of one company for the last 50 days. That is called time series data. On one single day, the stock prices of 50 companies. That's a cross-sectional data. And in some cases, the combination of these two could be there, which is what sometimes we call it as a pooled data or even a panel data. This is a common name that is being used for. So probably it's like 50 companies for the last 50 days. That is what we are. It's a combination of both time series as well as your cross-sectional data. And depending on the type of data we are working with, we will do the appropriate analysis. Right? So we will be dealing with all these aspects. What should I do if a cross-sectional data is there? There are aspects like regression and all which we will do on a cross-sectional kind of a data. Right? What if the time series data is there? There is something called time series analysis which we will do if the data is more in a time series kind of a manner. So depending on how the data is organized, we will apply the appropriate analysis on that. And coming to the most important heart of statistics, called as the central limit theorem. What this theorem simply says is, let's say we are talking about a sample of size 1000. Right? As I said, when I asked you to measure the heights of some 1000 people, you came up with 160. I asked you to find out the heights of some 1000 people. You have taken some other random sample and you came up with 165. Someone else came up with 170, someone else came up with 155. What it says is, these numbers, whatever are coming out, 160, 165, 170, 155, these numbers, they follow a normal distribution. These numbers whichever we are talking of, the means, the sample means whichever we are collecting, the distribution of that sample means will follow a normal distribution whose mean is equal to the population mean with a variance equal to this much. The simple way of how you should